Transfer entropy is used to describe the amount of information transferred from one signal to another related signal. For example, two EEG leads located at different places on the head. More precisely, it is defined as the excess number of bits needed to predict the next value of one signal if you assume the two signals are independent instead of acknowledging that they are related. This entity has been used to correctly identify pathways of electrical activity flow in the brain and to locate focal zones of epileptic seizures. If we consider two signals A and B, such that the next value of A depends on the previous k, a number of values of A, and the previous m values of B, then the transfer entropy is given by this relatively complicated equation. But if we look in this equation, the numerator inside our log is the probability that the next value of A is a given value if our two signals are related. And the denominator is the same probability if A and B are not related, if they are independent. Let's take an example to make this a little easier to understand. Suppose that we have two people who draw a card from a fair deck of 52 playing cards. The first player, player A, tells you the suit of his card, and player B tells you the color, red or black, of her card. So player A in this example has a heart, and we know that player B has a red card. Player B then discards, and player A gets a new card, and then discards his old card. Predict the suit of player A's new card. In this case, player A could draw any card except for the heart that was in his hand. Therefore, the probabilities are those that you see on the screen. But suppose that there is a relationship between the two signals A and B. Specifically, player B gives her old card to player A, and then player A discards his old card to the deck. This information changes your prediction of the suit of player A's second card. We know that it was red, so therefore the probability of it being a spade or a club is 0. As we go through the summation that was in the transfer entropy formula, what we are doing is going through all the possible combinations of suit and color, and then thinking of all the possible outcomes that could happen for player A's second card. Here we have calculated what would be the numerator of our fraction, which assumes that the two signals are related. Here we have calculated the denominator, which assumes that the two signals are not related. And this actual probability goes outside of our logarithm in our equation. So these are all of the values for our equation. And when we plug them into this very complicated equation, we yield a transfer entropy of 52 over 51 bits for our example, which is approximately 1 bit, which makes sense because we gained one binary piece of information in this example, the color of player B's first card. The units are bits because the base of the logarithm is 2. So the transfer entropy is always a non-negative number with a value of 0 indicating no transfer of information. To determine the direction of net information flow, we need to take the difference between the transfer of entropy of B to A minus the transfer entropy of A to B. A positive value of this difference means that B predicts A. A negative value means that A predicts B. And again, a value of 0 means there is no relationship. When applied to two EEG leads at two different locations, A and B, a positive difference between them means that electrical activity at location B predicts that related activity will occur at location A. For example, this may be a pathway of cortical activation, Or it may be, if we have a case of an epileptic seizure, then location B may be the origin of the seizure, or may be recruited before location A.